We left off with the understanding that pressure causes flow and resistance fights flow. I want to explore this a little bit more deeply. We can draw a little chart, a little table that expands on this. I want to have 3 columns: flow, pressure, and resistance. And the first thing I want to do is say, well, I want you to have the hydraulic analogy in mind. So think about the flow of water, the pressure in water, and the resistance, like the narrowing of the pipe. Have that all in mind. But what I'm going to express here are the terms and the units that are used in electricity land. But the ideas should carry through. So first of all, there is a physics symbol for flow, and that physics symbol, and I do not know why, is the capital letter I. There's a physics symbol for pressure, which is V, and resistance is R. Now, when I say physics symbol, I mean physics particularly as it pertains to electricity. So V does not mean pressure anywhere in all of physics land. In electricity, that is what that means, essentially. There's also an electrical engineering unit, or these can also said to be physical units, but I'm sort of drawing a little bit of a false distinction between physics and electrical engineering. It's not so. They're not like in a war or something where they're arguing about units, but I think it'll be useful just to think about them slightly differently. So I'll say, an electrical engineering unit. The unit of flow, these are called amps, and that the symbol for an amp is the letter A. The unit for pressure electrically is volts, and I am giving you the plural here, and the symbol for that is the letter V, and the unit for resistance is ohms, and the symbol for that is not a Latin or a Roman letter. It's actually a Greek letter. It's the capital letter omega. The lowercase omega, by the way, looks kind of like a script, like a curly Q kind of W, if you're familiar. So this is a capital omega. They chose that symbol because it sounds like the word ohm. Now, before I go on, by the way, these units have kind of funny names: amps, volts, and ohms. They're actually all named after early electrical discoverers, and that feels kind of like it makes sense because they were all discovering new things, and these things simply didn't have names. So it's as if you were like walking in a field and then you like see something that's unlike anything you've seen before. Well, if you found that thing, maybe that's going to be named after you. So a while ago, that's exactly what happened. And the amp is actually short for the longer version of this term, which you won't see frequently written out, is ampere, A-M-P-E-R-E. Those are named after André-Marie Ampère. That's my poor attempt at a French accent. Volts, those are named after Alessandro Volta. That's my poor attempt at an Italian accent. And ohms are named after Georg Ohm. That's my poor attempt at a German accent, because all of these early discoverers happen to be in Western Europe. So those are where those names come from. Now, just something that is kind of to help give you a sense of scale or proportion. I'm going to say unit size. So just to give you an idea, an amp is a very big unit. Like 1 amp is kind of a lot. So I'm going to say that's like an elephant. You can have 1 elephant. You could have 2 elephants. Already that's a whole lot of elephants. So if we talk about 1 amp, let's like, oh, that's kind of a lot of flow. A volt, it's more like a cat. Like you could have like 5 cats in a room. Like that makes some kind of sense. You could have like 30 cats. That would start to be a lot. But, you know, you could have some number like that. An ohm is like an ant. It's a really small unit. So you could actually have like many, 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 many ohms. That would be a normal thing. We're going to talk about like 10,000 ohms, and that's not weird or unusual. We are not in this class going to be dealing with 10,000 amps. Definitely not. That's like the combined output of like a power plant. And we're not going to be talking about 10,000 volts. That would also be coming out of a big power plant as well. So huge unit, medium-sized unit, small unit. Now let's relate these units to each other. So what we said before is pressure causes flow. Pressure causes flow. The way I'm going to describe that is in a more symbolic way is I'm going to say I, this I here, flow, is proportional to pressure. Flow is proportional to pressure. Resistance fights flow, right? So I is proportional to the inverse of resistance. That's the number 1. I is proportional to, so more resistance is less flow. Less resistance is more flow. So this is really just a restatement. Pressure causes flow. Resistance fights flow. I've just restated it in more symbolic terms over here, but nothing up my sleeves. Nothing has changed. And now finally, we actually can combine these two statements. And we can say the following. I equals V over R. What that says is flow equals pressure divided by resistance. And it turns out that that is the case in terms of fluid and in terms of electricity. This is frequently stated, V equals IR. And if I were to draw a little box around that and want to label it, I would label it Ohm's law. Ohm as in ohm. So this is actually a confusing way of stating it to me. V equals IR. I don't really understand, like the pressure is the result of multiplying the flow by the resistance. This one makes more sense to me. If you have a certain amount of pressure divided by a certain amount of resistance, that will give you a certain amount of flow as a result, as a consequence of what's happening over here. So now, next video, we're going to learn about how to actually do some mathematics to use this understanding, which I hope we've arrived at through explanation, not just through me handing it down and saying this is the truth. I hope it makes some kind of sense to you and it feels kind of right based on the way that we got there. But now we'll be able to just basically insert some numbers and do the math and solve some problems that are relevant to our actual electrical engineering practice.